Hello. I wanted to show you a simple example. No, just kidding. It's a hard example, but I'm going to try to make it simple. Of an object that has an initial velocity and speeds up. Okay? So I'm just making up an example here. Let's say you're sitting on the side of the road and you see a car go by two telephone poles. Okay? Here's the first telephone pole right here. Okay. Telephone pole number 1. The car is already moving. And then sometime later, the car is going even faster past telephone pole number 2. And let's say the distance between the two telephone poles is 108 meters. Okay. So let's say you know the following things. You know that the car's displacement is 108 meters. So what we mean by that is from where the car starts to where the car ends is a vector. And that vector has a length of 108 meters. And we know that the car is speeding up with a constant acceleration. Now, in real life, you might hear the car smoothly speed up, and then you know it's constant acceleration. In other words, the car is changing its velocity the same amount each second. If you're looking at the speedometer would be moving smoothly. It would be moving at a constant rate every second as the car speeds up with constant acceleration. All right, and I'll give you a time. Let's say you happen to look at your watch and notice that this event for the car to go 108 meters takes exactly 6 seconds, okay? And I don't know, its initial velocity somehow, you find out that the car was moving with a velocity of 3 meters per second. Okay? So initial velocity at 0 seconds, is 3 meters per second. Okay? These are the things that are given. You should probably think about the types of things you could solve for. What kinds of things can physics help us figure out about this situation? Go ahead and pause the video and think about that. I'll keep going as though you paused the video. Let's see here. What could physics help us find? Well, I suppose when the car gets to the second telephone pole, it'll be going much faster. That would be our final velocity. And we could certainly find that. And knowing our changes in velocity and knowing our change in time, I'm sure we could find what the acceleration was. So A equals question mark. And I should remind you that the acceleration didn't change. So I'm going to draw an arrow of the same length over here. All right, well, let's see how we can figure it out. Typical approach would involve drawing a velocity time graph. You should try that now. Go ahead and press pause. Try to draw your velocity time graph for this situation. I'll keep going as though you paused the video. Should look something like this. And this is your initial velocity. And this is your final velocity at time that we define as t. Okay? And you should know that this area is that of a triangle. And down here, we have a rectangle. Okay? The rectangle area is going to be whatever the initial velocity is. Looks like it's 3 meters per second. So this rectangle area is 3 meters per second times our time, which is 6 seconds. So I might as well label that on my graph right now. That time there is 6 seconds. Okay. My initial velocity I also know. Let me just clean this up a little bit. This is my final velocity at 6 seconds, which I do not know. My initial velocity looks like it was 3 meters per second, and this is a velocity time graph. And velocity would be measured in meters per second, right? So this would be V, meters per second, T, seconds, all right? And so 3 meters per second times 6 seconds gives me the area of that rectangle, which would be 18 meters, okay? And you could take this area here and make an equation for it. It looks like it's going to be our change in velocity. So the whole rectangle would be change in velocity times our 6 seconds, right? So 6 seconds times whatever our change in velocity is, that's the height of this triangle, is our change in velocity from beginning to end. But because we're not talking about that full rectangle, we're talking about a triangular shape, we're going to have to do 1/2 times base times height. So 1/2 of 6 times change in V. And just to make it simpler, I'm going to leave out the units. After all, I have them on my axes. So what was that? 1/2 6 times change in V. This simplifies to 3 change in velocity, 3 delta V, right? Now I'm kind of stuck at that point, so naturally I'll just go to an acceleration time graph. Okay? An acceleration time graph is going to be the slope of my velocity time graph. So it should look something like this, right? And this area is my change in velocity. Okay? And that's going to be calculated by whatever my acceleration is, I'll call it A, times 6, right? 6 seconds. So 6A is my change in velocity. I can just take this and substitute in here, right? And I know that the triangle and the rectangle together, this entire area, looks like it's 108 meters altogether. So I can use that relationship to find my acceleration. Okay? So I'll do that now. The area of the triangle plus area of that rectangle together has to give me 108. And I'm going to leave out units at this point, okay? So 108 is equal to, what 3 delta V? That's what my triangle is. Except in place of delta V, sorry, I meant here and not here. In place of delta V, I'm going to put 6A, all right? So I got 3 times 6A, which is my acceleration, plus the area of my rectangle, which looks like 18 meters. Together, that has to be added to make 108, and that's meters, obviously. So then 18A, that's 18 times my acceleration, plus 18 meters has to equal 108. So if I take away 18 from both sides, let me take out those units right there. It's kind of confusing. If I'm not going to show units, I should be consistent about not showing my units. Okay, so that was 18, is that right? Yeah, 18 meters. So 18A plus 18 meters equals 108. So I subtract 18 from both sides, right? And I get 90 on the right-hand side equals 18A. Divide both sides by 18. I get acceleration equals, is that 5? I think 5 times 18 is 90. So this is going to be 5 meters per second. 1 second. This means that each second our car speeds up or changes velocity by 5 meters per second. And that's the slope of our velocity time graph. Now, I would probably want to find my final velocity as well. So let's do that. Let's see. We have a relationship right here. So change in velocity is equal to 6 times my acceleration. So change in velocity is going to be what, 30? 6 times 5 is 30, right? Because 5 is my acceleration. So in other words, my velocity in the end minus my velocity in the beginning is going to be 30 meters per second. So my velocity in the beginning, it says, is 3 meters per second. So final velocity minus my beginning velocity has to equal 30, right? Final velocity minus my 3 meter per second initial velocity has to equal 30. So that means my final velocity is my 3 meter per second initial velocity. I'm going to put units on all these because this is so much simpler. So my initial velocity plus my change in velocity, which was 30. And altogether, this means that my final velocity is 33 meters per second. So that's a pretty nice, more difficult problem. And hope you enjoyed it. I'm going to now make another video showing you how to do the same problem, but in a completely different way. All right. Hope you enjoyed it. Have a good night.